Hello there. My name is Andrew Bridges with Photron USA, which is a wholly owned subsidiary of Photron Limited of Japan, the world's largest manufacturer of high-speed video cameras for slow-motion analysis of events that occur too fast for the unaided eye to see or to understand. But today I wish to talk about our high-speed 2D polarization camera, the CRYSTA, and how it can be utilized to image stress distribution in additive manufacturing and other production processes. We all appreciate the glare-reducing benefits of polarized sunglasses, and you've probably all seen the normally invisible crazy patterns in automotive and architectural glass while wearing them. Well, this is stress, and it is intentionally induced to ensure, should the glass break, it will do so in a controlled manner and not shower us with razor-sharp shards of glass. But polarization can also be utilized to show us a phenomena, sometimes referred to as photoelasticity, that can enable us to understand what is taking place beneath the surface. Digital image correlation, infrared imaging, and conventional high-speed cameras, to name just a few, let us see what occurs on the subject's exterior. But if you want to see what is taking place within the object, beneath the surface, then we need to get creative. This video, recorded with the CRYSTA high-speed polarization camera at 7,000 frames per second, shows how stress is distributed when a piece of transparent acrylic is machined. The second video shows how subjecting the same test piece to ultrasonic vibration during the cutting significantly reduces the stress. How else could you so clearly demonstrate this improvement? Crystalline materials can be classified as either isotropic, where refraction is symmetrical, so the same regardless of the direction of the light passing through the material, for example glass. Other crystalline materials might be anisotropic, meaning they have a physical property that has a different value when measured in a different axis. Wood is a great example of an anisotropic material, as it has two distinctly different axes and is much stronger along the grain than across it. Sodium chloride and calcite are also good examples, where light is refracted into two rays, known as either the slow and the fast, or the ordinary and extraordinary rays, that are dependent on the refractive index of the material. One of these rays will travel slower than the other. This timing is defined as the retardation and is typically measured in nanometers. Birefringence, or double refraction, is the optical property of a material having a refractive index that depends on the polarization and propagation direction of light. As mentioned, the CRYSTA is a high-speed 2D polarization camera. To make it, we took your common or garden high-speed CMOS sensor, comprising of 1024 wide by 1024 high, 20 micron square pixels, with the necessary circuitry to enable it to operate at the full 1 megapixel resolution to 7,000 frames per second, and by reducing the resolution, we can increase the frame rate to over 1 million frames per second. Then we sputtered a pixelated polarizer array made from photonic crystal directly onto the sensor on a pixel by pixel basis. This photonic crystal lattice features pixels in clusters of 4 square, with each pixel having a different polarization axes at 0, 45, 90, and 135 degrees. By applying phase shifting algorithms with circularly polarized incident light, birefringence, phase difference, and azimuthal angle can be measured to enable us to quantify and measure physical stress in transparent or semi-transparent solids and fluids in high-resolution, high-speed detail. Traditional polarization systems often utilize a single-point measurement or rotating or moving polarization filters. This prevents them from being able to capture full-field two-dimensional data. By bonding the photonic crystal polarizer lattice directly to a high-speed CMOS sensor, with our pixels offset by 45 degrees from their immediate neighbors in the 2x2 polarization clusters, we can simultaneously expose all pixels at hundreds, thousands, or even millions of frames per second, and with very short duration shutter times if so required. As mentioned, birefringence is the optical property of a material having a refractive index that depends on the polarization and propagation direction of light. The anisotropic birefringence is often quantified as the maximum difference between refractive indices exhibited by the material. Retardation values that can be determined by the phase difference of the X and Y components show the internal stress within the sample being tested and are relative to the material thickness and the photoelastic constant of any material being viewed. In this setup at NIST, it shows the CRYSTA in our traditional testing configuration, which comprises of the CRYSTA camera connected to a lens, in this case a Leica Z16 APO microscope lens. The subject, in this case one of NIST's 3D printers, is positioned between the camera and the lens, and a circular polarized 530 nanometer LED light source. Lastly, a laptop running our Photron Stress Viewer Windows software. Here we see three different aspects of two passes from the same NIST test recorded at 60 frames per second with the CRYSTA. The results show the birefringence changing as the polycarbonate cools. Test specifics are layer heights are 300 microns with 400 micrometer internal diameter nozzle at 280 degrees centigrade and around 30 millimeters per second feed speed. As you saw in the last slide, as well as being able to display the retardation in nanometers and the principal axis orientation in degrees, we can also display the retardation across a user-selected line within the recorded 2D data, time-space, which is the retardation as it changes across a user-defined line, and the values of any point in the displayed image. And of course, all this data can be exported as comma-separated values to a spreadsheet. As with all Photron high-speed cameras, the CRYSTA can be easily synchronized to external timing systems or hardware. Here, a FLIR infrared camera system is synchronized with the CRYSTA to help better understand the correlation between temperature and stress distribution during PLA curing. Equally easy, the CRYSTA can be integrated with a wide variety of other lab systems. Here it's shown connected with Anton Parr's modular compact rheometer, the MCR301. Production of plastic optical components is a growing area of research where both our dynamic CRYSTA and wide-range high-resolution area scan systems are seeing great use. As long as the material being studied is birefringent and transmits a minimum of 30% light, the CRYSTA and its static scan brethren can be used to visualize both dynamic and/or residual stress. With lightweight plastics playing an ever-expanding role in a wide variety of fields, the ability to assess and understand how these materials perform is critical. Here we see a polymer film being stretched and recorded with the CRYSTA at 200 frames per second. The CRYSTA can be utilized as a key component in a Fizeau interferometer, in which the interference of two beams of light is employed to make precise measurements in optical density. Utilizing the CRYSTA as a key component of the interferometer, it is possible to visualize sound. This video shows the sound from percussion castanets recorded at 100,000 frames per second. The graph at the top is from a microphone producing very limited and strictly two-dimensional data. This recording shows sound waves being reflected from a plate position at 45 degrees to the source and recorded at 40,000 frames per second. Interferometers are widely used for the measurement of small displacements, refractive index changes, and surface irregularities. Lastly, we have expanded the polarized sensor concept to cover larger scale scanning. This concept can be expanded to cover a production web up to 15 meters wide, utilizing multiple line scan cameras and illumination sources. This enables the engineers to see the effects of assorted production processes on the finished polymer for flat screen displays, solar panels, or similar end product. Thank you for your interest. Please feel free to contact me if you have any questions or would like to find out more about a high-speed or high-accuracy static scan polarization systems or software. Incidentally, we do have both types of system available for demonstration, loan, and/or rental. Thank you very much for your time.